Hello, everyone. I'm Yadu. I'm with Parsl and Globus Compute team, and I'm going to talk about Parsl scaling on Aurora. All of this work was basically done in collab with our friends at the ALCF. So when I talk about scaling, first we need to take a look at this list. So we talk about leadership scale. So that means we are looking at the tippy top of the supercomputers in the known world. So El Capitan, Frontier, Aurora, these are big machines. And the important number that I want you to look at here is the number of nodes that these machines have. So roughly, I would say top 3 machines, the biggest machines that we care about right now, they have roughly 10,000 nodes, and that's the scale that we are targeting with Parsl. So like I said, we have friends at ALCF. They have generously contributed lots of computing time to us. So we'll be focusing for this talk, we'll be focusing on Aurora and all our scaling efforts on that machine. So Aurora is an interesting machine in that it has got 2 CPUs. It's got 6 GPUs split into 2 tiles each, so that you have 12 GPUs, essentially. And it's also, it consumes a lot of power. So I think it consumes like 22 tons of coal's worth of energy in an hour. So we'll come back to that. It consumes a lot of power to keep a machine running. So metrics that matter. When we talk about scaling and performance analysis, we have to look at what metrics we care about. So throughput, obviously, we care about that. Especially for fine-grained workloads, this is pretty critical. Like how fast can you pump tasks? But importantly, you have to also look at like what are our throughput targets? What scales do we want to be measuring at? Latency matters maybe a little bit less because it comes into play when you have lots of tasks with lots of dependencies. For now, for this talk, we are going to focus on tasks with no dependencies, just bags of tasks. And the last one, and I think personally the most important one here, is node/worker utilization. Meaning, if we have a lot of nodes on a big machine, can we keep the entire machine busy with minimal wastage? Right. So configuration and specifics of what we are going to look at. Now, this config that I've got on the screen right now, it's coming from the documentation at ALCF that's hosted by the ALCF. They've done testing, extensive support for this stuff. Now, 3 pieces here. The configuration is going to use the high throughput executor for the rest of the talk. We're going to just focus on that. This configuration uses the PBS Pro provider, and it uses MPI exec to launch managers onto every node in the batch of nodes that you've provisioned. Now, for this experiment set that I'm going to talk about, instead of the PBS Pro provider, we are using an alternate config that's also on that website, but it instead uses the local provider. The reason we do that is we are doing a bunch of heavy lifting. We do not want to be impacted by other stuff that's happening on a login node. If you're running in the PBS Pro mode, like you're running on the login node, we want to have better isolation. And so that's why we are switching and we are using the local provider for these experiments. Okay, cool. A little bit more info on the experimental setup. Like I said before, we are going to be using the local provider with the MPI exec launcher. We'll basically use a weak scaling study, and by that, what I mean is we'll get n nodes, each with 12 workers, because Aurora has 12 GPUs, so 1 worker per GPU. And that means that we'll get 120,000 workers at 10K, roughly, of nodes. Each of these nodes, or each of these workers, we are going to try and put 10 tasks on each. So that's how we'll set up the workload, and we'll modulate the task durations from 0 to 100 seconds. We'll do a bunch of tweaking of different things in the Parsl config, like with logging, a little bit of prefetch, setting address specifically, a few different things. The first thing, and I think probably the biggest takeaway from this talk is basically on this slide here, logging and monitoring. There is this option we have which turns off logging, and the numbers that we see with the green and yellow, green and orange, where we hit 8,000 tasks per second, that's only with that's possible only with logging disabled. With logging enabled, you see that line far below, which is like 800 tasks per second. So it's like an order of magnitude difference if you have got logging enabled. So if you care about performance and you do not care so much about monitoring and logging, please turn it off. Otherwise, you're not going to get these numbers, which is sad. Engineering effort is needed to fix that, but that's for another time. The second piece is one of the tunables that we discussed quite a bit in the paper, the original Parsl paper, is prefetching. Basically, what you do is you batch up additional tasks when you send out tasks to the manager. So you reduce the communication from the Parsl interchange to the managers. Turns out this doesn't really matter anymore. ZMQ is pretty efficient. Unless you are looking at very tiny tasks, like close to 0 seconds or less than 1 second, prefetching really doesn't do very much. So the default of prefetch 0 is good enough. So you do not need to really fiddle with this tunable anymore. The last, okay, again, we are getting close to time. Okay, the important bit here is this, reaching saturation. So this is the important bit that we need to focus on. How quickly can we saturate the machine? So this plot is for 2048 nodes, 100-second tasks, and we are trying to saturate the machine. We can sort of see that there is this rapid spike up to try and fill up the machine. There is about 4 minutes that we take in order to fill up the machine. From then onwards, we just keep the machine full. And you can sort of see that, around 1,000 seconds, that's the ideal make span. And we just go over by that by about roughly 4 minutes. Now, this is, again, this plot is a little bit odd in that we do not actually have 8,000 nodes. I overloaded 2,000 nodes with 4 managers each, which means that you should take this result with a little bit of a grain of salt, or like a lot of it. But the point here is that we are able to saturate 8,000 nodes. From Parsl's perspective, from the interchange's perspective, it doesn't matter if it's actually 8,000 nodes or if it's just 8,000 managers that connect to it. We can fill up the machine in 11 minutes. But that means that the machine is burning power while we are trying to fill up the machine. So that basically means that at 10K nodes, we'll estimate approximately 30 minutes to fill up the machine, and that's 5 tons of coal. So the point is that we need to optimize that. There is room for improvement there. So again, based on everything that I just discussed, if you want to tweak the config for better performance, here are a few things that you could try. So for example, you could set address to the specific interface that has the highest bandwidth on the machine. So especially, we didn't talk about data. Like these tasks are running without any data going back and forth. If you set it to bond 0, you probably will have the highest bandwidth you can get. Set prefetch to 0 because it doesn't really matter. One important point here is that MPI exec override, which says no abort on failure. If you do not set that, if any node fails, crashes, runs out of memory, it'll bring down the entire job. So if you set that, rest of Parsl will just continue chugging along, ignoring that fault. The last one is, again, initialize logging is equal to false so that you can get the nice throughput numbers. How are we on time? Okay, we are very good on time. Next steps. Okay, so as you can see, this is like very early work. There is lots of extra stuff that we could do, we would like to do. We want to be extending the scaling test to full machine scale, impact of like parameters and results on the performance. So run experiments with data going back and forth. We have to look at the CPU and memory overhead on the interchange side and also on Parsl. So there is lots of things to do. If you have ideas, please come to me. If you would like to do this eval on your machine and you have spare allocations for us, please ping me. And I guess I've got the link to a repo here. And I would just finish with that acknowledgements. Lots of thanks to the ALCF team for like giving us support and like allocation to do all of this work.